I'm not dividing by capital N, where capital N stands for complete samples, number of samples. Okay, so it's the number of samples which are completely spread over this sheet. Say if this is my sheet, then I have n number of samples on this sheet. Out of that, I am just interested in y equal to yj. Okay, so this particular strip, and where I know in this strip I have samples only rj. So you can see here I am dividing by rj. So nij by rj is conditional probability. Okay, so that is the case if I divide say nij by n. What will be this probability? Can anybody elaborate? Just speak out. If nij by n, what is the difference between these two? Anybody? So if I want to write nij by n, I will write x is equal to xi, comma y is equal to yj. It means this is a joint probability. So this is equal to x is equal to xi and y is equal to yj. I should write like this. Then I can say if I have to satisfy these two conditions, both should exist. That is x equal to xi and y equal to yj should exist. Then I have to have nij by n. So this is a joint probability, whereas this is the conditional probability, where you see my domain is squeezed from n samples to rj samples. I am just interested in rj samples when I say conditional probability. So that is the difference between the joint probability and conditional probability. Now similarly, I can write in reverse way. That means I have written here condition is x is equal to xi. X is equal to xi. So probability of y is equal to yj given that x is equal to xi. Probability that y is equal to yj given x is equal to xi. So in this case, condition is x is equal to xi. That means I have to consider now this vertical strip. So my domain has been squeezed from n samples to ci samples. What is ci? Ci is the number of samples in that particular column where x is equal to xi. Okay, so again, when I say conditional probability, my domain has been squeezed to ci. So you will see that I am dividing by ci now. Then what is the chance that y is equal to yj given that x is equal to xi? Then number of samples are same. That is, I am just talking about this particular cell where n is equal to nij. So nij by ci is the conditional probability, or probability y equal to yj given x is equal to xi. So if I proceed like this, I can write this equation based upon the earlier definitions. Now you see here, suppose I write probability of x is equal to xi, comma y is equal to yj. That means I am talking about joint probability, which is equal to nij by n. So that we have seen just now, nij by n. So this is talking about complete domain. Okay, then what I do, I divide nij by rj and multiply by rj by n. I just take this nij from top and divide it by rj, and then rj by n. I just try to do some arrangement. So what has happened is this particular portion nij by rj is probability x is equal to xi given y equal to yj. And what is this probability? rj by n? Rj by n is probability y equal to yj. If you recall your previous some rule, then y is equal to yj is equal to rj by n. You can check here, y equal to yj, that means I am interested in all these samples. So I am not interested in value of x. Irrespective of x, what happens if I choose y equal to yj? Then whole these samples, the count is rj, where the value of y is equal to yj. So rj by n is probability of y equal to yj. Okay, so we write probability of x is equal to xi, comma y is equal to yj. This is equal to these two quantities. This is relative quantity multiplied by y equal to yj. So similarly, we can play with this with respect to Ci. Instead of dividing by Rj, suppose I divide this Nij by N by say Ci, what will happen? Now Nij by Ci into Ci by N. So actually Ci get cancelled. So I am just playing with this again. So when I play with Ci, it becomes probability y equal to yj given x is equal to xi into probability of xi. So this is probability of x equal to xi, and this is the probability y equal to yj given x is equal to xi. Okay, so this is just same thing, and this is also equal to probability x equal to xi comma y equal to yj. So these two equations, equation 1 and 2, they are same. I can equate 1 equal to 2. If I do that, I can rewrite this as probability of x is equal to xi given y equal to yj. This is equal to probability of y equal to yj given x equal to xi. So just flipping of these two terms into probability of x equal to xi divided by y equal to yj. So I am equating 1 to 2, and this term I am keeping to left hand side, and this second term is divided to this. That's it. Okay, so that will go into denominator. So this is called as Bayes rule. This is very famous Bayes rule, which is probability x equal to xi given that y equal to yj. So this is the condition y equal to yj, which is equal to probability of y equal to yj given x equal to xi. So this is important, given x equal to xi into probability of x equal to xi divided by y equal to yj. So this is very famous Bayes theorem or Bayes equation. You must have seen in maybe 12th class. You might have seen in the form of a's and b's. Say probability of a given b, you can write probability of b given a into probability of a divided by probability of b. So these two things are same. But when it comes to pattern recognition or machine learning, we are going to follow this particular terminology. You note down this. The left hand side of this Bayes equation is called as posterior. Okay, why it is called as posterior, we will see. So left hand side, this probability is called as posterior. This probability is called a likelihood, like this. This is called as prior, and the denominator is called as evidence. Okay, the denominator is called as evidence. So this is a very beautiful simple equation actually discovered by Bayes. So name is Bayes theorem in 16th century. So you can see this is a very old rule. Even computers were not present that time, but that rule is still helpful in predicting class of the objects. Now I just rewrite this equation which is used in machine learning. So I will write all the terms here which are used in machine learning. So probability of omega, suppose I given x, this is equal to probability of x given omega I. Don't worry about this. I will repeat all the terms. What are the meanings of this? Okay. So this is the same equation. If you see Duda's book, it will be there maybe on third or fourth page on itself only. So now here omega stand or omega I stands for ith class. The capital X stands for feature vector. Okay. Capital X stands for feature vector. Now the first term, that is probability of omega I given x, stands for you are being provided a feature vector x and you want to predict what is class of this. For example, suppose I have extracted height and width of the object. I have measured height and width of an object, and then I want to say whether this is pen or duster. I will call pen as omega 1 and I will call duster as omega 2. So what this probability is trying to say, the left hand side, you are providing some vector x. Suppose x is equal to 0.1 and suppose 0.1 centimeters is let us take some realistic number. Say 10 centimeters is height and 0.5 centimeters is width of the object. Now you are being asked if this is the feature vector for a given object that computer has seen, tell what is this. This is the question. So what we do is we find out the posterior probability, that is the predicted or you can say probability or some kind of a prediction based on probability, which is called as posterior, that if this is the x, then what is this? Given condition is x. You can see from this line onwards, what is condition? You are being provided capital X vector and you are asked what is chance that this is omega 1. So I will say here probability that given object is pen provided that input is x. Then I will calculate probability that given object is duster provided that input is x. And suppose my probability here is 0.7. So obviously this will be 0.3 because sum is always 1. In this case, since the chances are more with pen, so my decision will be pen. Okay, is this understood? If you want, I can repeat, but you have to speak out. Is this fine?
Yes, sir.
Yes. Yes, go ahead. Go ahead. Is this fine? Okay, so there is no reply, so I assume that it is fine. So probability that pen is 0.7 and probability that it is the duster is 0.3, then I will go with max probability. So max between them is 0.7, so my decision is 0.7, and my decision is that the object seen by computer is a pen. Okay, so this is posterior. Now posterior decision is based on likelihood into prior divided by evidence. So what is prior? First of all, we will see prior. Prior is the thing for a given problem domain. When you start training your machine, you collect samples. Suppose you have collected 100 pens and you have collected 50 dusters, or a computer in general is going to see pen more than dusters. Okay, these are number of pens you have and these are number of dusters you have. So what is chance that if you pick up randomly any object, it will be pen? So I just say it is 100 divided by 150. So probability of pen is 100 by 150. What is probability of duster? So probability of duster is 50 by 150. So this information is called as prior knowledge or prior. Okay, so what is prior? Prior is before I do anything or any kind of prediction, whatever knowledge I have with the problem domain for given classes, I can write in terms of their respective probabilities. So that is my prior knowledge. Okay, now see what is likelihood. This is very important. What is likelihood? Likelihood, as I said, is probability of x given omega I. Now you must understand the difference between probability of omega I given x and probability x given omega I. If this is clear, then everything is clear. So rest of the course is very simple. But you must understand these two concepts. One of them is posterior. So this is posterior. So what is posterior? You are being provided some feature vector x, and then you are trying to predict class. So when you predict class, then it is posterior. We are doing some prediction business. What is this object? What is this object? If this is the feature, what is this object? So that is called as posterior. Now what is likelihood? Likelihood is the probability of seeing a feature, given feature in particular class. Now see what is difference. Now these are some samples which are collected for pen, and these are some samples say collected for duster. Okay, now when I say probability of x given pen, so this is my complete problem domain where these pens and dusters are lying. So when I say given pen, the condition has been squeezed from complete problem domain to a small domain of pens. Okay, so this is my interest. So within this pen domain, what is chance that I will see some x is equal to say 10 and 0.5. Okay, so if I do my computation of probability with respect to certain domain, then it is called a likelihood within that domain. Now when I say probability of x given some duster, so x is again same, say 10 and 0.5. Then what I'm going to do is I'm going to check this particular domain, because here my given domain is duster, so I will just check this duster domain and see that what is chance that I will get here 10 and 0.5, this particular sample. Okay, so when I take likelihood, it is talking about specific class, say pen class or duster class. This is not predicting anything. This is not giving you a decision about prediction. It is helping you to take the decision, but that will not give you the decision. Decision is always computed based on Bayes prediction. So that is posterior. Okay. So we will take the example so that these things are more clear. Now let us take this example. So there are some apples and oranges, and there are two containers, container 1 and 2. So container 1 consists of 6 oranges and 2 apples. Container 2 consists of 1 orange and 3 apples. Okay. So probability of container 1, probability of picking this, there are 2 containers with you, and it is observed that a person, say sitting over here, a person sitting over here chooses container 1 more because he is near to this than the container number 2. Okay, so container number 2 choice is, say for example, he picks 10 times one of the containers, then he is choosing 6 times container 1 and 4 times container 2. So that is meaning of this probability of 1 and probability of 2. Now question is, if one object is randomly selected, what is probability that it is an apple? Can you solve this? If one object is randomly selected, what is probability that it is an apple? And the second question is, if a randomly selected fruit is orange, what is chance that it belongs to container 1? So these are 2 problems you have to solve. And this will clear your basic about posterior and likelihood. Now let us try to solve question number 1. If one object is randomly selected, what is probability that it is an apple? So we are not caring about from which container it is appearing to me, but I am just interested what is chance that it will be an apple. Okay, so the hint is use sum rule. Now I can use this sum rule. So here you can use sum rule like this: probability of apple, because I am interested in apple. What is condition? Given the container is 1. Since I am not interested in container, what I am doing is I am adding the probabilities for container 1 and container 2. So see what is done: probability of apple given container 1 into probability of 1. So choosing the or selecting the container 1, what is probability of that? So that is getting multiplied. Now same is the case with second container. So probability that I will get apple if I select container 2 multiplied by selection of that container. Now you can see here there are 2 apples in this container. There are 2 apples, say here and here, and there are 8 objects. So when you choose container 1, probability of getting apple is 2 by 8. But what is chance that this particular container itself is selected is 0.6. Okay, so this is 2 by 8 into 0.6. Then there are 3 apples in container 2. So the choice of getting apple is 3 by 4 multiplied by 0.4. That is how many times I select the container 2. So if you solve that, chances of getting apple is 0.45. So you try at home the second problem. If I say find out probability of orange. You can solve in the same way and calculate answer for this. Okay, instead of apple you will put there orange and then you solve like this. Ideally answer should be 1 minus 0.45. Since probability of orange and probability of apple added together should be 1. So it should be 0.55. You check this whether this is coming or not. Okay, so I have done that for you. You can check that this is 0.55. Okay, you can try at home. Now question 2 is little bit tricky. If randomly selected, I don't know from which container it is appearing. I have selected some container and then I have selected some orange. Okay, so that orange has come to my hand. Now my question is, what is chance that it belongs to container number 1? So I am now particular about the container. Now see how I design the probability here, how I compute that. So probability that orange is coming from container 1. So it is probability 1 given condition is orange. This I want to compute. So I don't know what is the probability. So I just use Bayes rule, because this quantity, left hand side quantity, is directly not computable. You cannot compute or not possible to compute this left hand side. So probability of 1 given orange, this is not possible directly from that diagram. So what we can do is we can use Bayes rule where these two quantities are flipped. So now you see here probability of orange given container 1, right? I can calculate this. Probability of container 1 I know, probability of orange I know. Okay, then I can calculate what is probability of 1 given orange. So this is the beauty of Bayes. You can flip these two variables. Since these two variables, say 1 given orange, probability of 1 given orange computation is not possible directly, we use Bayes for this. So Bayes is very good in doing this kind of flipping of the things and calculating the probability. Now see here, directly I can substitute the values. Probability of orange given container 1, I know that there are 6 oranges out of the 8 fruits. So 6 by 8, then I know what is probability of getting container 1. So this is the case. Then I know what is probability of orange that I have calculated on the last slide. So it is 0.55. So if I substitute everything, then I know that the chance that it is the orange coming from container 1 is 0.82. So chance is that it is coming from container 1 is equal to 0.82. Now similarly I can calculate the probability that it is coming from second container. So container 2 given orange. So I am again interested in finding the probability that it is coming from container 2, and I have in my hand orange. I don't know from which container it is coming, so I am calculating these two things. So by substituting proper values here, that is probability of orange given container 2 into probability of 2 divided by probability of orange. So this is going to be calculated like this. So probability of orange given 2 is 1 by 4, since there is only one orange in 4 fruit of container 2 into multiplied by 0.4, that is chance of container 2 divided by probability of orange. So these two things are same. Okay, denominator is same. So if you substitute, it is 0.19, and you can check that the sum of these two must be 1. Okay, so if you see here, it should be 1. So this error might have be seeing might be there due to some rounding error, but rounding of the numbers after this. So, but if you check it, sum is always 1. Now, what is my decision? Whether I should go with container 1 or container 2. To minimize my error, I will stick to the decision of max probability. That is, I will declare that if I get orange, it is coming from container 1. Okay, since 0.2 is the chance that it will come from container 1, and there is only 0.18 chance of container 2. Okay, so to minimize my risk, I will go with this. Okay, so that is the decision. Then we will go for this particular problem with 3 variables or 3 classes in next class. So I will request all of you to revise your probability knowledge little bit, that is required for subsequent classes. Okay, so let us stop here.